Welcome to the lecture for Wednesday, January 22nd. We'll start off by finishing up some material on the addition of angular momentum and isospin, and then we'll talk about nuclear burning in stars. So let's recall what we did last time. We talked about when we have two particles, one with spin J1, another one with spin J2, and we put them together into a combined system and talk about the ways that these spins of these two particles can combine together, how they rotate. I have two particles and I rotate both of them. It turns out that I get irreducible pieces of these spins rotating together. In particular, we said that we start off with the largest possible spin being J1 plus J2. Then we can drop down to J1 plus J2 minus 1. And then we can keep going down by ones until we get to J1 minus J2. Technically, you should have an absolute value here. Okay. Now, the example we did last time was that when we have two spin 1.5 particles, when we put them together, we could have spin 1 or spin 0. So remember how we went through the process. It took us a while. We started off with the highest possible value of m, and then we said that was the state 1, 1, and that turned out to be 1/2, 1/2 with 1/2, 1/2. And then we used the lowering operator acting on it and got 1, 0. Okay. And then we identified that with 1/2 minus 1/2 with 1/2, 1/2, added together with 1/2, 1/2 with 1/2 minus 1/2. Now if we did the lowering operator again, and that's what we did, we ended up with 1 minus 1, and then that ended up being 1/2 minus 1/2, 1/2 minus 1/2. We said there were a total of 2 times 2, because there's 2 states for the spin 1/2 here, 2 states for the spin 1/2 here. 2 times 2 is equal to 4. And so we should have a total of 4 states. There's one more state here that's orthogonal to all 3 of these, and that's when we take these 2 guys and subtract them rather than adding them together. And that state will have spin 0, at j equals 0 and n equals to 0. Okay. And we can check that this actually really is spin 0. Now, in general, we can do this addition of angular momentum, putting together 2 particles with spin and decomposing them into what are called the irreducible representations. Okay, and so this process of decomposing the additions of angular momentum is what's called angular momentum addition, and the coefficients are called Clebsch-Gordan coefficients. Okay, so here is, well, these days we can read off the Clebsch-Gordan coefficients from a piece of software like Mathematica. That's very convenient. But if you want to use a table, here's what the typical table looks like. So if we want to do spin 1/2 with spin 1/2, what we just discussed, the notation is we have the m values for the first one and the m value for the second one, and you can read off the coefficients in this little rectangle. Okay, and then these are the j m values that you get for the different irreducible representations. So for example, spin 1/2 with spin 1/2, if I want to look at the plus 1/2 state, the 1 plus 1 state is equal to 1 times that state. Okay. Now, there's a little bit of a notation here that they don't write the square roots. So if you see, for example, minus 8 over 15, it's actually minus square root of 8 over 15. And so that's why in this table they write 1 over 2, 1 over 2, 1 over 2, minus 1 over 2, rather than putting the square roots in. That's just a little shorthand here. Okay, so then you can take a look at how the angular momentum addition works for all the other possible spin states. And this is, by the way, the notation that's usually used. So if I have the total spin J m with, when I add together spins J1 with J2, then the decomposition of this element in terms of the original two particle spins, m1 and m2, that's what's written here. Okay, that's the notation for these Cauchy-Gordon coefficients. All right, now the idea of the spin 1/2 system was actually quite a very elegant system, where we have two possible spin states, plus 1/2 and minus 1/2. And by the way, I should mention that the rotations spin 1/2 system actually has its own name. We've been talking about the group SO3, but it turns out if you restrict to looking at the spin 1/2 system, this actually is another group that's very similar to SO3. It's what's called SU2. That's the special unitary group. So special, remember, means determinant equal to 1. Unitary means that the matrices U dagger is equal to U inverse. So these are 2 by 2 matrices. So let me write this out. So the SU2, that refers to, if you think about SO3, the representation with J is equal to 1/2, that defines another group called SU2. Now, as you might expect, the algebra for the SU2 and SO3 turn out to be exactly the same. So then you might be wondering, what exactly is the difference between the two? Well, it turns out that the only real difference between SU2 and SO3 is that in SU2, if you do a rotation by 360 degrees, you don't get back to the original state. You actually get -1 times that state, whereas if you do a 360 degree rotation for SO3, you get back the same state. Okay. Now, this group SU2, or the spin 1/2 representation of SO3, it was very elegant, and in 1932, Heisenberg realized that there may be another instance of this SU2 group, but this will have to do with the similarities between the proton and the neutron. So the proton has a mass of about 938.28 MeV, and the neutron has a mass of 939.57 MeV. Very, very similar masses. And Heisenberg realized that these could be treated as spin up and spin down states in a different sort of way, where the proton is spin up and the neutron is spin down. But if we call them spins, that would be totally confusing, because they really do have spins. So he called them isotopic spin, or we just for short call them isospin. So the proton then would be, and the neutron would, these guys together, these nucleons collectively, belong to an isospin 1/2 system, where the plus 1/2 is the proton and the minus 1/2 is the neutron, where isospin up is the proton and isospin down is the neutron. Okay, so this is what's called an internal SU2 symmetry. It's an approximate symmetry, but it's a very good symmetry. And so now you can talk about, when you put together a proton and a neutron, what types of isospins you could have. And this is the same problem as we've been discussing. When we put together two spin 1/2 particles, we have spin 1 and spin 0. So when we put together a proton and a neutron, when we talk about isospin, we can have isospin, so let's write it as I. It can be 1, or the isospin can be 0. And it's the same Cauchy-Gordon coefficients that you get. So we can have proton with proton, okay? You can have proton with neutron in the sort of symmetrized combination, we can have neutron with neutron, and see these give you the isospin 1 combination. Then we can also have this combination where there's an anti-symmetry between the exchange of the plus 1/2 and the minus 1/2, and this gives us isospin 0. Now the deuteron is the only stable 2-nucleon system, and that corresponds with the isospin 0 state. If you were to ask what is the spin of the spin of the deuteron ends up being 1. So J equals 1, but isospin is equal to 0. So this idea of isospin representations can be applied to heavier nuclei. In particular, we can talk about different states that belong into different representations across different nuclei. So let's say, for example, fluorine 18, which has 9 protons and 9 neutrons. The ground state of the system is a 1+ state, the spin 1, and positive parity, that's what the symbol here means. And so this ends up corresponding with a state with I equals to 0. Okay? The fact that there are no other states that is partnered with is a strong indication that I equals to 0. Well, technically you can always say that I must be greater than or equal to 0, but the fact that there are no other ones tell you that is I equals to 0. Now then you can go up to look at the 0+ state, and you find that there are 2 other states, the 0+ state of oxygen 18 and the 0+ state of neon 18, that are very similar in energies to the 0+ state of fluorine 18. And so this belongs to a multiplet with at least I greater than or equal to 1. Similarly, we end up seeing that the 2+ state also, we end up with 3 states, and the 4+ state we see these 3 states as well. So these guys all belong to some representation of isospin that is greater than or equal to 1. So that's the end of the lecture on angular momentum addition and isospin. We're going to now transition to talking about nuclear burning in stars and the proton-proton chain. This lecture is adapted from slides by Sonak A. Chaudhuri from the University of Birmingham. Okay, so let's talk about the forces involved in steady-state process in hydrostatic equilibrium in a star like our sun. So let's consider just simply a little element. Let's draw a little element. Let's draw like this. That has a surface area dA and has a radial thickness dr, and let's say it is at a distance r from the center. So we think of this some spherical object, a spherical shell. Okay, and so there's going to be the force of gravity. Okay, let's just say also that the mass of the little element is dm. We're going to have the force of gravity that will pull towards the center of the star, let's say the sun. And let's do a little calculation of what this this force would be due to gravity. So first of all, we need to know how much mass we have within this radius. So remember, with this inverse square force law, like gravity, we see all the mass that's within the radial distance that we are probing. So let's say capital M of r is the amount of mass we have within this sphere of radius r. Then the force of gravity that will be pulling this element towards the center will be equal to Newton's universal constant g times the mass of the star up to that radius times the mass of that little element, so g m1 m2 divided by r squared. Okay. Now, let's think about what would, if this is really steady state, and that's the assumption that this element is not just falling in, but is actually being held up by something, and what would be holding that up? It would be some pressure coming from the burning process, the nuclear burning process. And so in order for that to hold up this element, we actually need a pressure difference. We need that the pressure on the top end has to be less than the pressure on the bottom side. Okay, so then there would be an outward force due to the difference in pressure. Okay, so I need a difference in pressure, dP, the difference between the pressure on the inside minus the pressure on the exterior side. So dP, if I multiply that by the surface area dA, that gives me the force due to the difference in pressure. Okay, so that's what I need to balance off this force of gravity. I need this to be minus F. Okay, now let's work with this a little bit more. dm is going to be equal to the density of the material out here. Let's say the density at radius r is rho of r. So it'll be the density times the volume, which is going to be dr times dA. Okay, so now let's put these together. So I said I have dP dA is equal to minus F is equal to minus G mr rho dr dA over r squared. And what I'll do is I'll write this dP as dP dr times dr. Okay, so now I'm going to take these two sides and I'm going to let me put the dA here, and I'm going to cancel out the dA, and I'm going to cancel out the dr, and I'll end up with exactly what's written here. dP dr is equal to minus G m of r over r squared times rho of r. So that's the steady state equilibrium, hydrostatic equilibrium equation that the density, the mass, and the pressure must satisfy. Okay, so now a star like our sun, the pressure near the center is about 2.5 times 10 to the 16th newtons per meters squared, or 2.5 times 10 to the 11th atmospheres. The temperature of the sun is about 2 times 10 to the 7th kelvins. Now, we can also use a different unit for this. If I'm converting into electron volt is about 11,600 kelvins. And so this temperature of the sun, 2 times 10 to the 7th kelvins, is a bit less than about 2,000 electron volts in energy. Okay, let's talk a little bit about how we express masses. So in atomic nuclei, we usually express the mass of the nucleus in what are called atomic mass units, U. And that is, by definition, it's defined as exactly 1/12 the mass of carbon-12. It's just a convenient way to define the mass because it's rather easy to measure the mass of carbon-12. Okay. There's a picture here of the nucleus. This is not to scale, clearly. This is, well, because the nucleus is much smaller than that of the atom, but it's sort of trying to show that the neutrons and the protons have a much larger mass than the electrons. So a carbon-12 atom has 6 protons, 6 neutrons, and 6 electrons. And therefore one atomic mass unit, is about 1.66 times 10 to the minus 27 kilograms, or about 931.5 megaelectron volts over c squared. So the proton will have a mass of about 1.007 U. A neutron will have a mass of about 1.009 U. and an electron has a mass of 0.0005 U. So much smaller than, about a factor of 2,000 times smaller than that of the protons or neutron. Now, it's worth noting that if I add up 6 protons, 6 neutrons, and 6 electrons, I don't get 12, as you might expect. I actually end up with 12.099. Okay. So why don't I end up with 12? What's the difference? Well, the difference is in the binding energy. So the mass of an atom is not equal to the mass of the individual particles added together. There's also the binding energy associated with the nucleons, as well as a bit smaller the electronic binding energy, but that's quite a bit smaller. Most of the binding energy is in the nucleus. So we said that the carbon-12 atom, when we add 6 protons, the masses, the 6 neutron masses, and the 6 electron masses, we get 12.099 U. So the mass difference between 12 and this is 0.099 U. And that corresponds with about 92.2 megaelectron volts. And that is the binding energy of the carbon-12 atom. Now, this binding energy is actually important in that when we have a process like nuclear fusion, this binding energy, there's going to be a release of energy because of the reduced energy of the bound system. So if I start off with 2 protons and I form deuterium, then because the rest mass of the deuterium is less than the rest mass of the sum of the rest masses of the protons, there is a release of energy. Okay? And in fact, if I work it out, so that these are 2 protons, this is a proton and a neutron, and by the way, there is something non-trivial that happens here. One of the protons has to convert into a neutron, and this happens through the weak interaction, where a proton converts into a neutron, as well as a positron, which is an anti-electron, as well as a neutrino. The symbols are nu E, and this is written as a E plus. Sometimes you also see it as beta plus. And the amount of energy released here, the difference between the mass of 2 protons and the mass of the deuteron, the positron, and the electron neutrino, there's a release of 0.42 megaelectron volts. There's a further release of energy when this positron annihilates with one of the electrons that came along for the ride with the protons in the hydrogen atom. So here's a schematic plot of the binding energies drawn like this, because the binding is a negative energy, a reduction in the rest energy. Okay, so this is the binding energy per nuclear particle versus the mass number. And so you can think about fusion as taking 2 smaller nuclei, putting them together to form a larger nucleus, which will have more binding per particle, and so therefore there will be a release of energy. That's nuclear fusion, and that's what happens inside of stars. There's also another process that's called fission, when a larger nucleus breaks apart into smaller pieces, thereby increasing the binding energy per particle and also releasing some energy. However, but this process is quite a bit different. This is related to the fact that this is a larger nucleus, there are more protons here, and the repulsion between protons is crucial for inducing this instability that fission resolves. Now, let's do just a very simple estimate of the energy scales and the time scales for our sun. So let's suppose we could convert the entire mass of the sun into energy. So the mass of the sun is about 2 times 10 to the 30 kilograms, and the rest energy would be then just mc squared, 3 times 10 to the 8th squared. Multiply these together, you get 1.8 times 10 to the 47 joules. Now, we can estimate the current luminosity of the sun, then you can estimate that by measuring the intensity of the sun's radiation at the location of the Earth, and then we can then multiply by the entire surface area of a sphere at the distance of the Earth-Sun distance. Then that will give us the total luminosity, and it turns out to be 4 times 10 to the 26 joules per second. So if we take this 1.8 times 10 to the 47 joules and divide by the luminosity, we get a time that's about 10 to the 13 years. So that's how long, if everything was converted to, all the rest mass of the sun was converted into energy, that's how long it would take. Now, fusion does not end up end up converting all of the rest to energy, just a small fraction. So we have 0.1% of the mass converted to energy. Then the sun would last, well, you just knock off a factor of 10 to the 3, you get 10 to the 10 to the 10th years, and so that's about 10 billion years. So that's a good estimate. We note that the sun is currently about 4.5 times 10 to the 9th years old. Yeah, so we found that nuclear energy is sufficient to sustain the sun's luminosity, but can it actually happen in the sun? What's the mechanism through which this happens? So in the sun we have, start off with a lot of hydrogen. So hydrogen is, and hydrogen atom is a proton with an electron. Okay. So you can imagine burning this hydrogen to helium, where helium, and it's more stable in the configuration, helium-4 has 2 protons and 2 neutrons. So if we go from 4 protons to helium-4 plus some other stuff, we find that we can release about 27 mega electron volts of energy. So, but how does this all happen? So let's just think about the energies involved. So first of all, we have Coulomb repulsion between these protons. So the Coulomb force, the Coulomb potential we know is 1 over 4 pi epsilon naught, Z1 times Z2, the charges, times E squared over R. So if I draw the Coulomb curve, now out here the nuclear force is essentially 0, okay? But eventually once we get about 1 femtometer, about 10 to the minus 15 meters, the strong force becomes dominant. So in order for fusion to happen, we have to be able to overcome this Coulomb barrier that goes up to about an MeV at about a distance of 1 Fermi. 1 femtometer is a Fermi. Okay. So how can we overcome this barrier? Well, the sun has a temperature of 2 times 10 to the 7th kelvins, we said. So let's calculate what is the temperature required to overcome this Coulomb barrier. Now, the point we're making is that the protons must have some energy. The system has to be hot. If the system is cold, then we have less energetic particles, fewer collisions. But if the system, if the gas or plasma is very hot, then we have lots of kinetic energy and more collisions. So now let's consider statistical mechanics to try to understand what could be happening here. Okay, so if a gas is in thermal equilibrium with the temperature T, then the atoms will have a range of velocities described by the Maxwell-Boltzmann distribution. So that Maxwell-Boltzmann distribution tells you the number density of gas particles with a speed in between v and v plus dv. And that number density is going to be NV, so that's the symbol for the number density, times dV. Okay, so that will be equal to this factor of m over 2 pi kt to the 3/2 power. Okay, and this Boltzmann factor e to the minus mv squared over 2kt times 4 pi v squared dv. Okay, and so then we get that this distribution will be equal to So then we find that the most probable velocity will be v squared is equal to about 2ktm. That won't be all that useful, but the thing I want to mention is a result that hopefully you already know, that the average kinetic energy will be equal to 3/2 kt. And that's simply because of the equipartition theorem, stating that with this very simple distribution, that every degree of freedom will give us a 1/2 kt. So since we have vx squared, vy squared, and vz squared, we're going to have 3 degrees of freedom, so we get 3/2 kt. So now from this we can determine the temperature that we need. Okay. So to overcome the Coulomb barrier, we need that 1/2. So this is just the mass of the hydrogen times v squared. Okay, it must be equal to 3/2 kt, which must be equal to the Coulomb energy that we need, z1 times z2 e squared over 4 pi epsilon naught over r. And because these are protons, we end up with z1 is equal to 1 and z2 is equal to 1. And if the distance r will be 10 to the minus 15 meters. So we end up with a temperature of about 10 to the 10th kelvins, if you work this through. Now, that's a lot larger than the central temperature of the sun, which we said was about 2 times 10 to the 7th kelvins. Now, you might say maybe what happens is that the tail of the distribution, the Maxwell-Boltzmann distribution, is what drives this reaction. It's just those very energetic protons at the tail that gives you this, but that turns out not to work. Okay, so the average kinetic energy of the proton at this temperature is 2,000 eV, like we said. But the electrostatic potential energy at this distance of a femtometer is about 1 MeV. We can calculate what fraction of the protons have 1 MeV when the average is 2 keV, and it turns out from the Boltzmann factor it's about exponential minus 1 MeV over 2 keV. So that's the exponential minus 500, which if you punch it into your calculator is about 10 to the minus 216. It's very, very small. It's negligible. There will be essentially no protons at all in that tail. So that doesn't work. But what comes to our rescue is quantum mechanics. So one can do this very carefully by solving the Schrödinger equation and looking at the wave functions, or we can just make a sort of a back of the envelope, very simple estimate. And that's what we'll do here. Later we will do the more careful tunneling calculation later in the course. So in quantum mechanics, even though there's a barrier where the particle classically cannot penetrate through the barrier because it does not have enough energy, there is, however, in quantum mechanics a possibility that you tunnel through to the other side. And that tunneling is possible as long as you don't violate if you take advantage of the uncertainty principle. So in other words, you can tunnel through a distance that's comparable to your de Broglie wavelength. If you estimate delta px, typical px and lambda, so you can estimate lambda as this h bar over 2 divided by p. So that's the way we're going to make an estimate of this process. Okay? So the idea is that instead of having to tunnel all the way to 1 femtometer, all we have to do is tunnel to a distance given by the de Broglie wavelength of the protons at the typical de Broglie wavelength of the protons at a temperature of 2 times 10 to the 7th kelvins. So we can make that estimate. So if I have lambdas is h divided, Planck's constant divided by p, the de Broglie wavelength, and I can plug in the estimated momentum here, I get then something that comes out to be about 3.57 times 10 to the minus 7 meters. So that's much larger than 10 to the minus 15. So the protons don't need to get anywhere near 10 to the minus 15s. And so this is actually what happens, this tunneling process through the Coulomb barrier. And without this quantum mechanical effect, fusion would not actually happen in the sun or any other stars. So what reactions are we talking about? Okay, so we cannot have 4 protons just all come together and form a helium-4 nucleus and spit out some positrons and neutrinos. That's just very unlikely. It actually happens step by step. The first step is what's called the PP. Well, the whole process is called the proton-proton cycle. But the first step is that the 2 protons come together. One of the protons converts to a neutron. That's through the weak interactions. To conserve charge, obviously, you have to carry off some of the positive charge, and that's what the positron does. We have a positron which carries off some of the electric charge, but then we also have this this electron neutrino that comes out. Okay, and so what happens is we form then this bound state of a proton and a neutron, which is the deuteron. So the atom is called deuterium, the nucleus is called the deuteron, or hydrogen 2. Then the next step that what can happen is that you have another proton from the hydrogen atom. It combines with this hydrogen 2, okay, and then you then end up with helium 3, 2 protons, 1 neutron. Now, because it's a 2-body in state, we cannot have a 1-body abound, 1-body out state. That ends up violating conservation of momentum and energy simultaneously. You cannot have a reaction where 2 things come together and form one and conserve momentum and energy. That simply doesn't work. And so the thing that comes off is a photon, and that will conserve energy and momentum. Okay, so you can imagine having that happen over here as well. You form a helium-3. And then one possibility for producing helium-4 is that these 2 helium-3 nuclei come together, and then they release 2 protons, and they give you the helium-4. Then these 2 protons can come back through this channel here, and through this process, and cycle through again. So what I've just described is what's called the PP1 chain, where the first step is the 2 protons come together to form the deuteron, a positron, and electron neutrino. This step takes the longest of time. It's about 1 billion years is the typical time scale. The reason it takes so very long is because it involves the weak nuclear force, which is much weaker than all of the other participating forces other than gravity. Okay, and then the second step actually is very fast, where we just have a reaction involving the deuteron and proton going to helium-3, and release of the electron. Now, the last step that we've discussed in the PP1 chain is when the 2 helium-3 nuclei combine together, and that is somewhat slow because of the rather strong Coulomb repulsion with 2 protons here, 2 protons here. But it takes about 10 to the 6th years, which is a lot faster than the 10 to the 9th years for the first step. And you have then the formation of helium-4 and the release of 2 protons. There's also, for the second half of this reaction, there's other possibilities that can happen. You can have, I mentioned the branch 1, pp1 chain where the two helium-3s come together to form helium-4 plus proton plus proton. But you can also do it, form the helium-2 in a different way, and you can have branch 2 where you have, let's say you've already produced some helium-4, so there's some that have been produced in this branch 1 process. So now what you can do is you can take this helium-3 and hit the helium-4 and produce beryllium-7. Okay? So that's this process, but in order to conserve momentum and energy, you need to release a photon. Now, with the beryllium-7, now you can capture an electron. The electrons would have come from the original hydrogen atoms. And so this electron capture then can form lithium-7, and this will require a weak interaction that will produce a electron neutrino. Now, this process actually can occur two different ways. You can either go to the ground state of lithium-7, which would then have a release of energy, and this is the most probable branch of 0.86 MeV, or you can go to an excited state of lithium-7, which would release 0.38 MeV, which would be only about 10% of the time. Now, after you've produced the lithium-7, I know it's somewhat complicated here, but then you can combine with another proton, and that will actually take you to 2 alpha particles, or 2 helium-4 nuclei. So compared to the branch 1, which happens about 85% of the time, branch 2 happens about 15% of the time. If you think very hard about what other ways you can produce helium-4, another route, which happens only about 0.01% of the time, is that once you produce the beryllium-7, as we've discussed, from helium-3 and helium-4, the beryllium-7 can combine with a proton to form boron-8 plus a photon. And now the boron-8 is unstable with respect to the weak interactions, so it decays into beryllium-8 plus a positron and an electron neutrino. But the beryllium-8 actually itself is unstable with respect to the strong interactions. It falls apart into two alpha particles, or 2 helium-4 nuclei. And so this reaction happens only about a fraction a very small fraction of the whole pp chain. So that's the end of this lecture for Wednesday, January 22nd. If you have any questions, please send me an email. So remember that for attendance credit, please email to me a 250-word summary of today's lecture. Thank you.